So for each semicall, we have all the measurements that we want to bring into the analysis, which is just two. The within subset variables are two. It's the packet arrival time at the monitor, which I'll define a little more precisely. What does that really mean shortly? And then the flag that indicates whether a packet is voice or silence control packet. Now, the number of, that's not here. All right, must be on the next slide. Okay. Well, disappeared. Just looking at a number that was interesting. Disappeared. Okay. All right. Anyway, but back here, the number of packets with for a semicall goes from 0 in the basis division. You could say it goes from 0 because, well, the semicall, one direction of the call never even forms. That's just part of this whole little, small call thing. So you could say really there's some zeros there. Up to about 734,000 packets. Okay, remember we have to get up to a number like 1.3 billion or something like that. Okay, so within subset variables. Now, however, each semicall has, by virtue of its construction, of course, the call identifier. But remember, the call identifier is just simply, I hope I did say that, the call identifier is a concatenation of 4 variables: source gateway IP address, destination gateway IP address, port number assigned by the source gateway, and port number assigned by the destination gateway. Okay. And of course, it has the call identifier. So given that we have the identifier, and we don't, that's all we really need to, say, access that subset, then we no longer need the port number and the port numbers as between subset variables, because the port number has no bearing on the analysis whatsoever. It's just a thing that the gateway assigns. And so it doesn't have any bearing on the traffic or anything we're trying to do in the modeling. It's just something that allows unique identification. But we've already got that. So they're just formally between subset variables, but in fact, the subset variables that we compute and keep are just source, or that we keep, shall we say, is source and destination gateway IP address. Okay? However, there are other between subset variables that get computed, actually some of them right at the outset, as soon as we're starting, because we know we want them. And then other things that can get, this is a general rule. You find yourself computing between subset variables on the fly as you go. Because you say, you know what, I think this thing is important. And there are some things, as I said, there's some things you know are important in the very beginning, because actually that becomes part of the construction of this. That's part of the model architecture, for example. That's one reason, like the start times of the calls. But whatever it is, here are some between subset variables. One, which of course is important, as you might expect, the measured link direction. It's categorical with 2 values. So for each each semicall, we have whether or not it's got the PSTN as the source or the PSTN as the destination. The start time, the time of the first packet of the semicall. The end time, the time of the last packet. The duration of the call, end time minus start time. Number of packets. Let's stop right there. So what, you know what? I got a question. Okay, this time we have to give you an exam now. So just to be sure we're all on the same page here. So all right, so I have the start time, I have the end time. So why am I saying end time minus start time is between subset variable? I mean, you've already got that there. This is redundant. But is it redundant? Why would I put that there? Why would I put that on an R object? Sorry?
Because of the periods of silence that if you come here before.
No, I can. No, my point is I have the time of the first packet. I have the time of the last packet. If I want the duration of the call, which is end time minus start time, I say, okay, that's going to be on my R object too. Delay.
Repeat delay between when the packet is sent and when it actually starts.
No, I get. Oh no. No, I actually get, I can take on my R object the time of the first packet, or the time of the last packet, and subtract from it the time of the first packet to get the duration. It's just, is it redundant? Why would I put that on the R object? Or it doesn't have to be on an R object. Why would that be sitting around? Well, suppose I'm going to compute it, you know, 1,000,000 times, 1,000,000,000 times. You know, this is the sort of thing that when you're talking about what you actually compute and stick on a data frame, a lot of it, I mean, you have to, you know, one of the hardest things of all in, let's say, the use of R, but this has got to be true for any, you know, interactive language for data analysis or any kind of data analysis. It's like you say, it's designing, designing the structure, the data structure for those objects that you're going to be grabbing again and again and again and again in order to do your analysis. And you say, well, I had to really think hard about this analysis. One of the most important things, especially in the very beginning, is to try to figure out, you know, what kind of data structures do I want to have so that not only is the computation going to be faster, but your programming is going to be simpler. Because if every single time I want a duration, I have to go grab two variables and subtract it, not only is it going to take longer if I'm doing it repeatedly than sticking it on some object, also it's going to, you know, the code gets a little more complex because I got these two variables and I'm subtracting them. Now this is a trivial case, but it's just generally true. Yeah.
Often it's the case you'll be halfway through your analysis and realize there's some computations you're redoing over and over again with the same data that really might be better as part of your data structure. Do you have any heuristic for when you decide to go back and redo that data structure? Or?
No. I just, you know, you do it. You're absolutely right. You just, finally you get sick of it. I think that's what happens. You say, I can't do this anymore. This is idiotic. Because you keep saying, oh, it's going to take a little time to redo the data structure. And then, oh, yeah, it's going to change this and that, you know, and so it's painful sometimes. But then finally, it's, okay, yes, I know exactly what it is. When the pain of not doing it exceeds the pain of, you know, having to use it. Okay, so it's something like that. All right, so this is a small point, but I don't know. It's maybe I'm just getting it off my chest. This is like a, you know, a counseling session. What?
So do you ever find when you're doing these analyses that computation is cheaper than storage or network bandwidth? So for example, if the result of your computation results in more network transfers because you've extended the size of your structure, then maybe it's cheaper to just recompute it.
Yeah, that does come up. I mean, what the reasons are for that, I was just talking to somebody today, you know, we said, well, all right. It was more, though, that in order to carry out this operation, we'd actually have to merge two, you know, talk about data structures. We got one over here and we got one over here, but we had to access them both. So we said, you know, the person I was talking to said, you know what, I'm just going to, what we computed over here and sent over to here. I'm just going to compute it again. Yeah, so that sort of, everything comes up. You know, and you make all sorts of, you know, unfortunate decisions, and then, you know, in the course of moving, oops, everybody grabs their cell phone. It reminds me, I should turn mine off, although I don't have that same sound. But yeah, everything like that happens. I mean, it's chaotic, really. And so that's an important point about these. Well, there's actually another point here, which is that along these lines, actually, which is that, oh, it's a little bit different. We actually needed a call start time, and a call end time, and a call duration. In other words, I won't go into exactly why, but so when we talk about a call duration, in other words, what we're saying is, oh, in this particular case, we actually are going to take the two partners of a single call, and we're going to get a single variable for those two partners, okay? So the call start time and the call end time and the call duration come from the start time and end times of the two partners in a call. So now how you choose, I mean, I'm just saying, those are between subset variables. I mean, what should we ascribe this to? Should we ascribe it to, you know, it doesn't really matter because these things get dealt with, or it's the duration we're after, really. Well, no, sorry, the call start time too. But that sort of lives at its own object, so, okay. But formally, you could say, well, it's a, you know, it's a, these two things are between subset variables for both of the semicalls, but we're not going to use them, we're only going to use one copy of it, so. No, here it is. Number of packets goes up to 749,000. Okay. So these between subset variables, this is all very fluid. I mean, some are computed at the start and stay. Some computed on the fly as part of the analysis and stay. Some of them are computed on the fly and then they go because they didn't work out. Also, a lot of these wind up getting stored in the R global environment because you don't need, I mean, you only have one per subset. So if you only have 666,000 values, then that's not so big that you can't just stick it in R and put these things in, say, these between subset variables, make a data frame out of them. A number of them that you're going to be accessing repeatedly for the analyses. All right? Okay, now, let me say a little bit about the overall analysis so you'll know where we are in all this. So we actually had quite a few different divisions. We have this basis division that was the, you know, you could make a graph of this thing. You can't quite make it, it's not quite a tree. It's close to a tree, but it's not really a tree. But anyway, we have different, you know, they all emanate from the information in the basis division. Actually, I suddenly realized, no, okay. All right, there's a basis division. Then there's a thing we call a complete call division, which is, I'm not going to talk about the details of these, but there was another thing, a complete call division. And it, you know, and it was sort of, it repeated many of the calls in the original division, but because we you know, or the basis division, we actually used the basis division in analysis. That analysis was going on at the same time as analysis using the complete call division. So instead of sort of just going in and subsetting calls from the basis division that we wanted for the complete call division, we just created a whole new division. Okay. Then from the complete call division came jitter division number 1. We will talk about an analysis associated with that, and then jitter division number 2. Okay, so we're, and these are, all four of these things are about the same size. So it's like, you know, you get a large data set and we've just multiplied by 4. Actually, it's even bigger than that because there's another analysis thread that starts with a different basis division, but we're not talking about that. So the idea is that you say, well, I got a fair amount of data. It's not too much, but you're going to be increasing the size as a result of the analysis. Now, in terms of storage, as I mean, it's 3 times that. right? Because all these divisions, our default anyway is it's the Hadoop default. We make 3 copies of all these things. So there is kind of an implicit notion of, we tend to be unafraid to just sort of start, hogging disk. But we have cheap disk. That's the thing. In order to get the disk we need, it has to be cheaper. Money actually is a factor in all this, right? So we will put up with cheaper and a little bit slower because we've already had such an incredible speed up that we feel spoiled already. So that doesn't, but if we don't have space for what we do, that's a real problem. Okay, so so they were the divisions. The analysis threads were, actually we had to look at timestamp accuracy because people out there in the computer network literature, I mean, they're not going to put up with something that, you say you modeled arrival times unless you tell them, you show to them that you've got really accurate times and you haven't added a lot of noise because of an inaccurate process, because that's going to invalidate the real times. So we had to address that. Semicall arrival process, I talked about that a little bit. So we had an arrival time analysis. Semicall duration, we modeled that. Alternating transmission and silence interval stochastic process, there was a model for that. So these 3 things combined to be the thing that we use to generate traffic. Then there was an analysis of the live jitter, the jitter that actually occurred in the data. I'll explain why we had to do that as part of the analysis. It's not something that's usable. It was just more to validate what we had done. So there's a first live jitter analysis and a second one. And we'll be telling you about that. That's why I put that in red. I'm not going to talk about the rest of these because time is finite. And this one seemed to do a better job of illustrating the various things we want to illustrate in the analyses. And I guess I was just saying this, to optimize computation in R in any analysis, different analysis threads can each get its own data structure. That's something you do all the time. And that gets extended to R repay. It's no different. So different analysis threads, it can be very helpful to form, for a lot of reasons, to form divisions for each analysis thread. So the basis division were used for timestamp accuracy and the semicall arrival process. Here we actually just did say, okay, ignore the short calls and live with that division. Semicall duration, because, well, we were able to get a between subs, I mean, that's sort of that's a between subset variable that's modeled. So we're not even back at the division level anyway. Semicall duration came from 2, the complete calls. Oh, I forgot to put this down. That came from 2 also. And the live jitter analysis came from jitter division 1, and the second live jitter analysis came from 4. Okay, but now here, just to give you an idea what this is like in terms of time, here are some times for some of these computations associated with the basis division. So computation time basis division, that should be the title. Okay, so what did it take? Transferring the raw text files from just Unix flat files into the HDFS as text files took 1,238 seconds. Okay, so what, 20 minutes or something like that? Now, here's the thing. We actually did that from within R. So you can call repay code and carry out an operation like that. And it's just a bit simpler because then you don't have to sort of learn the commands. Jeremiah showed you some of the commands, but you don't have to worry about the commands that would do that transfer off in the Unix environment. You can actually call things from within repay, and it makes it easier. All right, then they're sitting there in the HDFS as text files. We now have to do 2 things. These are keep in mind, these are multiplexed. They don't come, by call, semicall. They come intermingled. So the code needs to identify the packets for each connection, assemble them, and then write them out as R objects by connection, okay? So, and when they come out, Jeremiah will talk more about this, when they come out, the packets for each connection aren't ordered, but we need them on the data structure to be ordered in time. So it's read them into R, which is a little on the costly side, demultiplex them, and sort. I guess. Did I get that task right, Jeremiah? Is that pretty much it?
What?
Read into R, demultiplex, and sort. Sort to get the times in order.
That's the reduce.
Yeah, no, I just want to get this, getting the R objects, that's the tasking. Yeah, I think that's right. Okay, so.
I'm saying that the sorting happens in the reduce step.
Okay, all right. Well, yeah, okay, all right. Okay, so now creating the basis division R objects, that was 2,714 seconds. Okay. Now, I can't emphasize how nice this is because, well, back before there was, we were using Hadoop, we had to have sequential algorithms that would separate these things, and it is, those are much more complicated. Okay, so Jeremiah will talk about this. So this was sort of nice to be able to just say, give me, have the map be, give me all the packets that, are, that are, or assemble them according to the unique values of the for tuple that identifies them. All right, now, then we have these between subset variables that got computed. Now that we have the basis division in R from them, we compute the between subset variables that we describe here. Again, going out and grabbing and doing the computation in parallel across all the subsets. So we get the between subset variables and put those, and those are in the, the result of it is in the HDFS. That's 86 seconds. Then reading the between subset variables into the R global environment was 84 seconds, and then forming a data frame that could be used for various things based on these between subset variables, that took 9 seconds. Okay. All right, so at least I will tell you that compared to things that we had to do before, this is a miraculous decrease in the amounts of time. So any questions about this process? So Jeremiah tomorrow will show you something about the code and the map and the reduce and things like that that did this specific operation. We'll wait till tomorrow, and we'll start out with that. Yeah?
I'm wondering about when you're reading in the text files, I'm wondering at what point you get to the key value paradigm.
So right after they go on, so the question was, at what point do you get to the key value paradigm? And then, since this is a map reduce job, we put them on the HDFS and they're zipped up text file. The moment you want to do a map reduce job, you have to have a key value paradigm. And the key value paradigm is provided by Hadoop for the case of text files. It's a file name and byte offset of the one. So right there, you're there. And then from that point on, we're saving value keys according to this description of the variables.
So is this is a presumption for the, the code itself that does this says it's my default, one line. That's a key. A key is a line.
A key is a byte offset at the start of the line. And
Okay,
that comes from
right.
Hadoop because you can't do anything in MapReduce without map paradigm.
Yeah, okay. All right. Okay, to answer your question, or? Okay. Okay. All right, any other questions?
There was one question. This was, what savings do you
Yeah. Well, that's a good question. All right, if you didn't hear it, so what about, putting these things in a SQL, database? It's a lot clumsier because, well, first of all, the question is where are you going to do the where are you going to do the computation? By the way, you can link all this up with a database, of course, if you have to. There's no reason why you can't do that, but that would be more, bring things in and then get them into the HDFS from there. See, so that's a different issue. You weren't asking that question, were you?
Just sort of, what's the benefit of using, what does Purdue bring to this that you couldn't get from a relational database as far as pulling out things and putting them into a MapReduce? Is it the the being able to use the run R and control both the data and these R executions using Purdue?
Well, the question is, if you're using a database, who parallelizes things for you? Appreciate that there's a lot of this that has gone on in the past. Absolutely, there's a whole suite of R commands that will link you up with MySQL. Okay, so people have coped with larger data sets in that way. And also what they tend to do is to see if they can't push some computations off into the database. Get the database to compute it for you. Well, that's not a nice way to lead your life. It just is, you've got the tremendous power of the R language that you would like to exploit for things and not have to be sort of doing a little computation here and some there. So I'm not sure it's, but again, Saptarshi implemented, he actually linked up HBase with FreePay, right?
I've never seen that.
Actually, now come to think of it, that's proprietary work. That's why we haven't seen it. Yes, that's right. That was for Docomo Research Labs. I think I'm allowed to tell you that. If not, just forget about it. Yeah, so obviously you can be pulling things in from somewhere else. We just used Unix flat files because for us it's so much more efficient. We don't want the overhead of some database management system, and that would be a typical thing. Although our data structures are, well, yeah, the raw data, it's not a problem. Once we get away from the raw data, we're finished. We don't have to go outside. So I'm not sure. I guess it's very clumsy to have to go into a database and be grabbing things from it all the time. You need a whole other set of routines that will manage that for you. And then you ask yourself, what do I get as a result of that? Yeah.
In addition to your point, some of the useful relational algebra concepts from database can be abstracted into a MapReduce framework pretty easily. So that helps as well.
Yeah. Okay. Because it's a parallel database?
Yes, you can, yeah.
Yeah, sure. Right. Well, that's a good point. But you still have to do the computation in the database. You still have to do the computation in the database.
No, I'm saying the relational algebra concepts of the traditional SQL can be translated into the equivalent abstraction in the MapReduce framework.
Yeah, I understand.
So you don't need a database, exactly.
Sorry, you don't need what?
The database. You can do what you
Oh, yeah.
do in the database in the MapReduce.
Yeah, right. Yes. Okay. Any thoughts on this, or Jeremiah?
Sometimes using MapReduce would be overkill, but it is possible to do the database concept in MapReduce.
And the only question I would ask is recombination, because R is so successful with sort of these flow of R objects that you manipulate either through functions or directly, and that's the success that we want to be a part of. So
Yeah, that's a good point. We seek to learn as little as possible about anything other than R. Okay, that's the game. Now the truth is, you do have to give some attention to, I mean, these repay commands need some attention. It does, you don't just say, go. You do have to think about the commands and do them in a way that's sensible. But of course, that's always been true in R. I mean, even with small data, you say there is an R programming style, and if you violate that style and start programming like you're writing something in Fortran, which was originally a big problem, with just do loops all over the place, you're going to get yourself into trouble very quickly, even with a small amount of data. So there is a programming style you have to pay attention to, both for making it easier for yourself and making your code much more elegant and streamlined, and making it run faster. Well, that's true with repay too. You really have to learn a bit about how to use it. So, but it's not onerous. So it's like anything else. And it's nothing like having to go outside and start writing code in Python and learn a whole new language. Okay, let's get back to the analysis. Okay, a link with multiplex traffic can only serve one packet at a time. Well, a link serves one packet at a time, that's it. So when a packet arrives for transmission on the link, it's served immediately if there's no packet in service being transmitted on the link, but it's put in a queue if the packet is in service. So in this queuing mechanism, the service time is the time it takes to write the packet on the link. And so each link has a speed in bits per second. In our case, we have each packet is 1,600 bits. And so it's the number of bits divided by the link speed. So if we have 1,600 bits, or if we take the 1,600 bits and transmit it 100 megabits per second, then the service time is 160 microseconds. But it's a queuing mechanism. And the queuing on the internet has been, widely studied. I mean, there's just thousands and thousands of papers on queuing. You might say, well, why? It's because of what comes in is, has such a dramatic effect on what the result of the queuing is. And mathematically, it gets hard very, very quickly. And so that's why we run simulations. So if the arrivals are all Poisson for the multiplex traffic, well, okay, but they're not. For the packets, the arrivals are Poisson, but the packet process itself is not. Okay. Now, so quality of service, this impacts quality of service quite a lot. So, so the source destination delay is the trip time of the packet from the source to the destination, and that needs to be roughly less than 150 milliseconds. The total queuing delay, the time of the delays at the routers, that's a critical component of source destination delay. In fact, it's the salient one. It's the thing that when things slow down, it's because it slowed down. Well, or you can have network outages, but aside from that, it's the queuing that gets you. So translating this into a queuing delay for a single router, that's a pretty complex matter. It depends on the network and so forth and so on. But safe numbers for an individual router is something on the order of a few milliseconds. There's also jitter. For voice traffic, actually real voice traffic, the jitter is, where people are actually speaking, jitter becomes a very important thing as well. So the packets, as they come out of the gateway, are supposed to be 20 milliseconds. So during a transmission interval, they're separated by 20 milliseconds. When they get to the other side, you want those to be relatively close to 20 milliseconds. But because they're experiencing delay as they go along, oh, I have to define jitter, don't I? Actually, sorry. OK, what is jitter? All right. So let's suppose that the arrival times of the packets to a queue are a sub I. So a sub I milliseconds is the arrival time at the output link of the ith packet of a semicall transmission interval. So a single interval, a sub I, is there's n arrivals, and a sub I is the arrival times at the output link, at the interface for the output link. All right. Now we're going to let d sub I be the delay in the queue for the interface on the output link. And we'll let e sub I be the exit time from the queue. Okay? Now that happens to be the time that we measure. So when we get packets, when we measure packets on this link on the global crossing network, it's the exit time from the gateway queue to get on the link, or if it's the other direction, it's the exit time when the first bit of the packet gets written on the interface from the IP router. Okay, so exit time, arrival time, delay, exit time. Okay, so A plus D is equal to E. The jitter in the exiting packets is J sub I is E sub I plus 1 minus E sub I. So you take all, for the interval, you take all packets in the transmission interval. If you have n of them, you're going to get n minus 1 inter-arrival times of those, and you want those to be as close to 20 milliseconds as possible. So we take that difference and subtract 20 milliseconds, and that's the jitter for I equals 1 to n minus 1. Now, if there's no jitter in the arriving packets at all, so that their inter-arrival time is 20 milliseconds, then the jitter is the difference in the delays. So difference in delays of second packets, of successive packets across across the internet is what causes jitter. And I don't seem to have that here, but basically something on the order of about 20 milliseconds is an absolute maximum you want anything to ever be delayed by the time you get to the other end, and the codec has to reassemble things. And so that translates actually on individual routers down to something that's fractions of a millisecond. Okay, so as I said earlier, the goal in collecting and analyzing these data was to develop a statistical model for the arrival times of the packets as offered load to the network. All right, offered load. It has to be the offered load. So what we needed to do, an offered load, let me say it again. It's the arrival times after packetization at the first link of its path across the network, which is the gateway output link. So the gateway finishes its job, and then it says, OK, I got to send it out to a link, and it sends it to an interface. So it's when it arrives at that interface, before any queuing that might occur in that interface, that's the offered load arrival time process. And that's what we need. Because the simulation generates the offered load, and then everything, the simulator takes care of any network processing that goes on. So we need pristine data. Okay? The problem is that our measured load is actually not pristine. because we're sitting there looking on the link. So for one thing, if it's packets coming out of the PSTN gateway, source gateway, the measured arrival times of the packets are the exit times from the output link of the gateway. So we've had a little bit of queuing that's gone on. So, you know, we're messing with these offered loads when we measure them. It's even worse in the other direction. When they come from Buenos Aires, then of course they've gone through many. That's the furthest other gateway, at least in terms of distance. They've traveled through the packets that come in from other gateways and have PSTN as a source. They've gone through many router queues on their path to the Newark link. So they've undergone the network processing of more than one queue, and in some cases, many more. All right. We need to verify that our measured data is a good approximation of offered load. What are our expectations? First of all, our expectation was, as you might expect, it was that actually the offered load really is pristine. It's just accurate, extremely accurate. It has virtually no jitter. There's an expectation. We also have an expectation that the measured arrival times will only have a small amount of jitter because at that time when we collected, the global crossing network was very lightly loaded. We knew that. So, for example, on the measured link, it varied between 2% to 11% in terms of, you know, bit rate of the traffic versus the link speed. So we had every right to at least hope for there being sufficiently small amount of jitter. But the only way really the only way to verify this is to actually analyze the live jitter of the live traffic and to look at it and see what its magnitude and see what its characteristics were. So this became, well, it wasn't the goal of the analysis, it was something that we had to demonstrate and verify so that when we told people, hey, here's the data we use, we could say, and this is a very good approximation to the offered load. And again, people in network research they're pretty hard-nosed. So you can't just sort of say it, you have to prove it. And this proves it. We did this analysis to demonstrate this. Well, of course, you know, we did it to see if it was valid. Okay, so that's the analysis that that's what we're going to describe. Okay, any questions about this? So you sort of see where we're going here. So we got to look at jitter. We have to analyze it. We have to see what its magnitude is. And we have to see whether or not it's conforming to what we would expect. It has to sort of do the right stuff. Otherwise, you know, then you have to call into question, you know, if this is making no sense whatsoever, then maybe there's something wrong with your data. Okay? So it's that kind of thing. Prove to me that these data make sense. So we already did prove timestamp accuracy, but other things can go wrong, clearly. I notice I don't have these numbers here. Well, 1.2 something or other. Okay, so the first step in the jitter analysis was to derive a jitter division, a first jitter division from the complete semicall division. Now, in this particular case, semicall now no longer has any relevance at all, because jitter is not about the call itself. Jitter is about the network. What's happening on those queues? These packets are coming through. You got two packets. They come through at about the same time. They're going to experience jitter. It doesn't matter what call they're a part of. It has nothing to do with the characteristics of the call per se. So for that reason, we're going to create a new division where now subsets are the arrival times and some other things. But it's a division. It's a division by transmission interval. Okay, and now we have 14 million subsets, because if you take all the calls and say, you know, what's the number of transmission intervals, then it's 14 million. The between subset variables are the arrival time of each jitter value. The jitter is based on 2 packets. So remember, it's a sub I plus 1 minus a sub I, or well, exit times. E sub I plus 1 minus E sub I. All right? So it's based on 2 packets. This a sub I is the arrival time of the first of the 2 packets. So these are the 2 within subset variables. However, there are some between subset variables actually that we had back on the semicall division that are relevant for each transmission interval. And what are they? Well, one is the source gateway. That's going to be, we know that's a factor. The source gateway for an interval and the jitter in that interval will depend on, will affect the jitter, because it means, if it's a source gateway that's further away, we expect to see more jitter than if it's something very close. The other thing that's important is the traffic rates. Actually, it's the traffic rates on every single router it passes through, but we only have traffic rates for one queue, and that's the one we measure. So but nevertheless, we will use that. So actually, okay, yeah, this is for the startup. We didn't actually explicitly get a rate. What we said was the following. We said, okay, I'll tell you what, we're going to be exploring the jitter as a first step. So we want, keep in mind, this is the mindset. We're just getting started looking at jitter. We've got these 14 million intervals. We know that source gateway is important. We know that traffic rate is important. We just need to take a quick look at it rather than getting in there and start getting, precise definitions of what we mean by the traffic rate that should impact the jitter. Let's just take a look. And so what we said was, okay, the traffic rate is changing with time. If we want to have a sample that has different traffic rates from small to large, then to sort of say visualize the data, what we'll do is we'll take a sample that stretches out through time. So I'm just saying that a sub I, the arrival time, provides a kind of surrogate for what the traffic rate is, because we will try to just go across all of the times, and then we'll be sure, space things out across time, because the rate on the link is going from 2 megabits, as I said, 2 megabits per second to 11 megabits per second. And so if we spread things out equally spaced at a reasonably fine interval, then we will cover all the possible rates as we look at what's going on in an exploratory mode as a startup. So keep in mind, you've just computed this thing, and you say, what's going on with these data? You're in the dark, okay? Okay, here's one thing to take a look at. How many measurements are there of jitter in each interval? This was something, now this is a between subset variable that we compute because we want to sort of start looking at the data. And we need to know something about how many jitter values there are in each interval. So this is we call this a quantile plot. I'll explain this in more detail. I'll sort of give you a little more background on quantile plots. But for the moment, I just want to say what this is. You take every single data point, like say this one here, and you get the fraction of values that are less than or equal to that point. So this is like an empirical cumulative distribution function, but the axes are reversed. So I go here. This is actually 1, 2, 3, 1, 2. This is actually the median right here. right there. So that's the median, because that's here at 0.5. So we draw that line showing the median. This is the upper quartile, and this is the upper 99% point. Okay? Here's the lower 1% point, 25%, 50%. Okay? So this sort of shows you the log, number of transmission interval measurements, and its log base 2. So we're going from, I guess, well, this looks like it's 1 right here. So this would be 4. And it goes all the way up to about, say, 4,000. Okay? So that's per transmission interval. Okay, now the reason for wanting to get a sense of that is because we need to take a first look at the jitter. So we say, okay, I want to actually make a display that allows me to study the jitter. And what we want to do is we want to take a collection of intervals. I mean, we've got 14 million of them. We have to pick. We want to display them. So what we want to do is we want to display jitter, j sub I, for each successive pair of packets, against the index. We want to just plot it. If you've got 50 of them, we plot j sub I against 1 to I equals 1 to 50. Just a picture to get started here. So again, this is this notion of, even though we have this large complex data set, we want to do some visualization at a detailed level. Okay, so we're going to sample these 14 million intervals and try to get something that is representative with regard to source gateway and representative with respect to traffic rate. So for each of the 27 source gateways, we selected 4 times 46 intervals. Actually, these data were only going on for 46 hours, not 48. Let's not worry about why at the moment. And we took the start time of each interval. Let's see, we selected 4 times 46 intervals, which means every 15 minutes for each source gateway. So 4 per hour based on the start time of the transmission interval. We wanted to have at least 50 jitter values. And then, so we had these intervals for each of the source gateways, okay? So each source gateway spread out every 15 minutes across time, and at least 50 values so that we get to see something. And we made these plots. That's what? How many plots are there? 4,968 subsets that are selected for this sample. Okay, so we're going to make 4,968 plots. And here's one for Rochester. Okay, so this is a transmission interval. As we go left to right, bottom to top, our index is increasing. So what's happening? You see something? I mean, if you're sitting there going, what the heck is going on here, then you get an idea of what it felt like when we first saw these. All right, so it's like, up in the upper left here, this is the first jitter in the interval, this is the next one, and so forth. Okay, well, let's do something here. Okay, so there we are at a peak. 1, 2, 3, 4, 5, 6, 7, 8, 9, back to the peak. 1, 2, 3, 4, 5, 6, 7, 8, 9, back to the peak. 1, 2, 3, 4, 5, 6, 7, 8, 9, back to the peak. Good heavens, what is going on? All right, so here's, you say, is this Rochester? Here it is again. Same thing, a cycle of 9, although the amplitude has gone down. Well, it turns out, I mean, you make all these plots. Actually, well, all right, you make a whole lot of plots, and then suddenly something just, it clobbers you. We did. I'm going to actually next time around we're going to talk about. I mean, you made 5,000 plots. I mean, that's crazy. It's not. It works actually, and I'm going to tell you why it works. I'm going to demonstrate to you that it works. And we're going to put these. Actually, these things will be on a website. You can actually look at what we had here, and you go look for yourself. And there's a number of principles that have to be adhered to in making. If you're going to make 5,000 displays, you better do it in a way that is sensible in terms of your ability to get through them rapidly. Because obviously, you're not going to sit here and look at these for 8 hours. You're going to have to be able to speed through them quickly. Okay? Well, you'll get to see these. You can take a look at them yourself and verify what we just said. But we saw this cycle of 9 in every single gateway, whether it was coming from Buenos Aires or London or Anaheim or Boston or Chicago or whatever. That cycle was there. Okay? So when you realize this, you realize, you know what? The only possible source of this are the gateways themselves. It's something about the gateway and the algorithms it's running to do the packetization. And so we contacted, and there was one supplier for all the gateway equipment. I guess I won't mention the supplier. Exact same equipment. And so we asked them, actually the Global Crossing people asked them why this is going on, and they said it's none of your business. Because that's proprietary information, it turns out. So they're not going to have to tell us what the algorithm is for the packetization. So, but something, okay? Now, and if you take a look at the magnitude here, it's on the order of about 0.4 milliseconds. You might say, does that matter? Well, maybe it does, maybe it doesn't. It's not huge. It's not, is it a big problem? But it's certainly something that suddenly a new thing enters the equation. All right? So what that said was that in analyzing these data, we now suddenly have a new source of variation that we need to take into account. We do need to pursue it. We can't just say, well, here's the jitter and it's not too big. That's not sort of making sure that everything is going right with these measurements. So what we did was we carried out, and this wasn't a costly analysis. It didn't take a huge amount of time. We did do it. But the time was much reduced, and it was a lot easier because we had repay and R. But now suddenly there's a new thing in the equation. It's that we have discovered through analyzing this first visualization of the data in an attempt to get a detailed view of the jitter. So we have not only as sources of variation the gateway and the traffic rate on the link where we collect, but we also have this other factor, which is the cycle of 9 coming from the source gateway. So we want to pull this apart and just have a quick look at it, and then, in fact, we've done this already, and report it out and say, well, this is what's going on, just to make sure that everybody is ready to believe that it's not our equipment. Actually, that was one thing we were worried about, whether or not the hardware that we were measuring with was the source of the cycle. So that had to be checked as well. Okay? All right, any questions or? Okay, so we're poised for the jitter analysis and what we did with that, and we'll show you. Next time we'll get into that, and Jeremiah will come and show you some of the Hadoop repay code associated with this. Okay, any questions? They told me to stop at 20:05, so I guess we're done. I'm not sure why the extra 10 minutes, but oh, yeah. There's Sergey. Okay, so we're done, Sergey. Anything you want to say, or? Okay. All right. All right, thanks.